Hi Honors Chemistry. This is the second part to chapter 16b. We're going to talk about strong bases and strong acids. We're going to talk about triprotic, polyprotic. We're going to talk a little bit about indicators too. So first of all, the definition of a strong acid or base is not the concentration. It has nothing to do with the concentration. Hydrochloric acid is a strong acid whether you have a 0.1 molar or a 0.0001 molar concentration of it, okay? So the concentration has nothing to do with strength. Strength is the amount of ionization, how much of it splits apart. In other words, the strength depends on the equilibrium constant. The equilibrium constant for something that splits apart 100% is so high it's not even recorded. It's just all of it. So if I have a 0.1 molar solution of HCl, I will have all 0.1 H plus ions, and I will have a 1 pH solution. If I have a 0.01 solution of HCl, I will have 0.01 H plus ions, and it'll be a 2 pH. Okay? So I hope I said that right. But anyway, all you have to do is memorize the list of strong acids. And I realize this year you probably don't have to memorize the list because I'm not going to test you like that. But any of you going into AP will need to know. Basically, it's HCl, HBr, HI, which are all right under each other in the halogens on the periodic table. HF is a weak acid, but HCl, HBr, HI are strong acids because those things have very high electronegativities. H2SO4, HNO3, and HClO4 are all very strong acids because these elements have strong electronegativities and they have a lot of O's. And that's a lot of detail that you'll learn even more in AP chemistry. But the reason that they're strong acids is because they have a weak hold on the hydrogen. So the hydrogen can be given off. So because they're so electronegative, the electrons are being hogged by these ions, which makes it easy for that H to just go away. It's not holding on to them. It's not holding on to the hydrogen as tightly as it could. These are strong bases. These are all ionic substances which dissolve in water, but you all know because of last chapter that the solubility product constant is different for everything. But these do dissolve 100%. So lithium hydroxide, sodium hydroxide, anything that starts with an alkali metal and has an OH is a strong base. Anything that starts with calcium and below with the alkali earth metals is a strong base. And they ionize 100%. So you won't see any Kas or Kbs, equilibrium expressions because they distribute 100%. So if I have a 0.1 molar solution of LiOH, I will have 0.1 OH ions, which when I solve for POH, that will give me a POH of 1, which means it will have a pH of 13. Okay? 13 is a very high pH number. The higher pH numbers, anything greater than 7 means something is basic. Anything less than 7 means it's acidic. Okay? So if I look at this now, and this splits up, 0.1, this is very important to remember, 0.1 molar of calcium hydroxide has 0.1 of calcium, but it has 0.2 moles of OH. Because when this splits up, you get 2 moles of OH for every 1 mole of calcium hydroxide. So this will be 0.2 molar. So when you plug it in to find the POH of this, you would have to do negative log of 0.2 instead of 0.1, and you would get a POH of 0.7. So when you subtract that from 14, you end up with a 13.3 pH. So watch out. For example, look at these strong acids. This is what's called a diprotic acid. Monoprotic means it's got one proton it donates. You check for that by the H's that are in front. Only the ones in front get donated. For example, acetic acid is sometimes written like this: HC2H3O2. You might say, well, what about those? Can't those get donated? No, because they're part of the acetate ion. This is a monoprotic acid because it only has one hydrogen it donates. So these are monoprotic. This is diprotic. There's an acid, H3PO4 is phosphoric acid, and that is a triprotic. So notice, mono, di, tri tells the number of hydrogens that are in front of an acid. Anything more than two you can also call polyprotic. Okay, poly meaning many. So that's how many hydrogens it can donate. Now, when it donates these, let's get this in some water, okay? And it is donating some, and I put both sides because you get equilibrium situations with weak acids. Anything that's not a strong acid or a base is a weak acid or base. So that means most of them are weak acids or bases. Organic ones are always weak, otherwise we couldn't drink them. Citric acid, vinegar, things like that. So this will give off one at a time. So then you have H2PO4, and it will give off one more, and it'll become this, and then it'll give off one more, each one becomes progressively weaker and weaker, okay? The equilibrium constant for this is higher, a lot higher than this or this, okay? So it goes one at a time. So this is the conjugate base of that. Because remember, the difference between a conjugate acid and a conjugate base is only one hydrogen. You never take both of them off at the same time. If you're asked what's the conjugate base of H2SO4, it would be HSO4 -1, okay? Because when you take away one positive, you're left with a negative there. So only add or take away one hydrogen when you're doing a conjugate acid or base. So that's why it takes 3 steps to get rid of all of your hydrogens with a triprotic acid. With a monoprotic acid, acetic acid is a weak acid, so you will get this acetate ion. And this, when we talk about buffers, is a buffer. Because if you look, Le Chatelier's principle says if you add an acid, it will shift this way and it'll relieve the stress. And if you add a base, it'll remove these and shift this way to relieve the stress. So Le Chatelier's principle is how a buffer works. And buffers are usually a weak acid and its conjugate base, or a weak base and its conjugate acid. And there are buffers in your blood to keep your bloodstream from getting too acidic or basic. And we'll talk about buffers a little later. Okay, so strong acid, strong base. The definition is they ionize completely. When you find the KSP of something like this, or the KEQ, whatever you want to call it, we usually call it Ka when we do acids. You have H plus C2H3O2 minus over, and you did some of this. This might seem familiar because there were some problems they used acetic acid on, I think, on chapter 15 review. So when you get the equilibrium amounts of those, that gives you the KEQ or the Ka. All right? The Ka, the K of the acid times the K of the base equals 1 times 10 to the -17 because it equals the thing of water. Okay, and that's why you can get the pH and the pOH will always, when I say 17, 14, not 17, fix that. So these two multiplied together will always give you this, and the pH plus the pOH which is just the exponents of these two. And when you multiply bases, you add exponents. Remember that from math? That equals that. Okay? So on page 419 are relative strengths of acids or bases. So when they ask you to compare which one's stronger, and they give you two, just look at that chart. On the acids, the ones near the top are the strongest. In fact, if you go through from perchloric acid, which is this, through nitric acid, they all say the Ka is large, which means they ionize 100%. Then you see the Kas, or the equilibrium constants of the other ones, and they get progressively smaller, smaller, and smaller until you get to the bases where the Ka is so small because it's technically a base. So that's what the chart you would use to determine. The bigger the Ka, the bigger the equilibrium constant of the acid, the stronger the acid is. Okay. Now, some things like water, you ever heard of something that's ambidextrous? They can use both hands? Well, if it's amphiprotic, that means it can act as an acid or a base. And we already saw from the last video that water can act as an acid or base. Water can donate a proton or accept a proton. So anything that can do that, in fact, we can look at this right here. This going this way can accept a proton, and this going this way can donate a proton. And this here can donate the proton. So this ion right here would be amphiprotic, as well as this one. This one can accept the proton and become that, or it can donate a proton and become that. So something that's amphiprotic can both accept and donate a proton, just like somebody that's ambidextrous can use both hands. All right, last but not least, measuring pH. Well, a lot of times in our labs, we just use a pH meter because that's a lot more accurate. It's electronic, it uses electrical signals because, look, H+ ions are positive, so you can measure electrical charge with that, and you can find the charges, and you can find the pH. But we also use indicators. There's all different kinds of indicators. I mentioned phenolphthalein. Phenolphthalein changes color at pH of right about 8, and it changes from clear to purple. But if you look on the top of page 425, it has the indicators, the pH range. So basically, if I have something of pH 6, and I want to see if it's pH 6, I would use methyl red and see if it's yellow, and bromothymol blue and see if it's yellow. Because if you look, the range at about 6.5, or at about 6, methyl red is yellow. But when you get down to 4 or 3, 4.5 or 5, it turns red. So what that means is that's its range. Anything, if you look at methyl red, anything below 4.5 is red. So you really can't tell. So you have to match your indicator with the range. And we usually do a lab where we use lots of indicators and see the different colors, and it's a shame. I'll try to find a video with that that'll help. But the pH ranges are all given on page 425. And so if it asks you what pH do you think this is, if it has this color with this one and this color with another one, just check that out and see and find out where that is. All right,